All right, we'll give people some time to get settled in here as we get prepared for this talk. See, we're already filling in. Just so everybody is aware, the chat will be down. If you have any questions, there is the option to utilize the Q&A. At the end of this session, we'll be posting the questions you guys have asked for Mike to answer. So as we're watching this, please feel free to submit questions. All right, excellent. We are filling in quite smoothly here. Okay. All right, we're going to get started. Good evening, everybody, and thank you for joining us for this Café Sci. My name is Dan Lavoie, and I'm honored to be your host for this evening. Café Sci is presented by PPG. Café Sci is also supported by the good people like you. Thank you to everyone who has donated to support this program. If you're unable to donate but would still like to support Café Sci, the most helpful thing you can do is invite your friends to join the audience. Café Sci takes place the first or second Monday of each month, and you can register for the next speaker at carnegiesciencecenter.org. Before I introduce tonight's speaker, I'd like to remind everyone that you can ask questions by using the Q&A button at the bottom of your Zoom window, and you can enter your question at any time during the presentation. All right, everyone, it is my pleasure to introduce Dr. Mike Brown. He scans the sky searching for and intensely studying distant bodies in our solar system in the hopes of gaining insight into how our planet and the planets around it came to be. In this quest, he has discovered dozens of dwarf planets and demoted one object to a dwarf planet, and is currently hot on the trail of Planet 9, a hypothesized body that is possibly the 5th largest planet of our solar system. So without any further ado, I'd introduce Mike Brown. Thank you so much for being here tonight.
Thanks so much, and thanks everybody for coming. And I have to say we were all a little bit late getting in here because we were all too excited to stare at the images, those very first images from JWST that just came down. I hope all of you were looking at them too. And if not, go check them out. The ones tomorrow, I think, are going to be even more amazing. But I will admit that JWST images are not the thing that I'm most excited about for JWST. It's going to be the spectra that are coming up soon. We'll talk a little bit about that at the end if we have some time. Before then, though, I want to talk about the search for another planet in our own solar system. There have been many discoveries in the last decade of planets around other suns, but the idea that there is another planet to be found in our own solar system, well, it's an idea that goes back hundreds of years, really. But it doesn't go back. It doesn't go back forever. It actually, if you were to go back to the year 1775, and you were to ask somebody to show you all the planets, they could do it. They could point out, if they had a good spot, they could see Mercury and Venus. You could see Earth. It's right down there. Mars, Jupiter, Saturn, and that's it. That's all the planets there were. There were no other planets known at the time, and people thought at the time that was all the planets that there were to find. As far as I can tell, I have not been able to find any speculation in those early days that there might be more planets to be found with telescopes. So it was a surprise several years later when William Herschel, with his new fancy JWST of the day, pointed his telescope up at the skies. He was scanning the skies, charting out where the stars were, and he found one star that wasn't quite like a star. It was a little too fuzzy to be a star, and that's okay. We see these all the time. They're galaxies, they're planetary nebulae. But he was careful enough to go back the next day to look at this fuzzy object, and he realized it moved. And the second he realized it moved, changed everything that we thought about the planets in the solar system, because it moved, and it moved so slowly that he could tell it was beyond Saturn. Now, at the time, he didn't really think that it was a new planet, because even Herschel, who had just discovered Uranus, was not convinced that there were any planets to be found out there. So he argued for a while that maybe it's a comet and it comes on an orbit that comes in close to the sun and goes further out, it was known that there are comets that do that. And what people really wanted to know is what kind of orbit did this body have? Did it go in a circular orbit around the sun like the planets do, or was it on one of these elongated comet-like orbits? And that question was hard to answer, but it finally got a definitive answer about 40 years later in 1820 by this Parisian astronomer, Alexis Bouvard, who wrote this very dry sounding book on tables of Jupiter, Saturn, and Uranus. And in these tables of Jupiter, Saturn, and Uranus, what he did was tabulate all the positions that he could find where people had measured Jupiter or Saturn or Uranus. He then calculated the gravitational fields of Jupiter and Saturn and figured out where Uranus should be and where it was. And one of the things he did, here's the math. You can check his math if you'd like.
Mike,
there it is.
real quick, can you maximize the PowerPoint?
Oh, you guys are.
There you go.
What,
Perfect. Thank you.
What were you saying? Were you just saying the screen?
Oh yeah, my apologies. It might not have grabbed it, but you're good. You're set now.
Let me try this. You were supposed to just be seeing this part.
My apologies.
You don't really want to see the rest of that stuff. Let's see. How does it look now?
There you go. Perfect. Thank you.
Okay.
Continue.
All right. So here's his math. Check it out. But here's more importantly, here is tables of where Uranus was. And you can see it goes the year he published it in 1820. Here's 1819. So you can go back and see all these observations of Uranus back and back and back. And then you get all the way back to, oh, well, actually, you get all the way back to before the discovery of Uranus. You get to 1769, 1750. 1690, the first observation of Uranus that Bouvard tracked down was actually 1690, nearly 100 years before it was recognized as being a planet. The astronomer who found it in 1690 never bothered to look a second time. If he had looked a second night, he would have seen it move and discovered Uranus, but he didn't. But with these observations all the way back to 1690 now, there's enough observations that Bouvard could tell it was in a circular orbit going around the sun, which is very exciting. So a planet, it definitely was. Also, what Bouvard noticed is sometimes it was a little in front of where he predicted it should be, sometimes a little behind, a little in front, behind, in front, behind for a long time, in front for a long time. Bouvard, being the preeminent theoretical astrophysicist of his day, said what all preeminent theoretical astrophysicists say: my theory is perfect, it's the observations that are wrong. You astronomers go do better. And so he admonished astronomers to do better. So they did. So they spent the next 20 years doing more and more careful observations of the position of Uranus. And it still was true. Sometimes it was a little in front, sometimes a little behind. By about 1840, pretty much everybody accepted that the reason Uranus didn't stay where it was supposed to stay was because there had to be another planet out there tugging it along, sometimes tugging it a little bit faster in its orbit, sometimes slowing it down a little bit more in its orbit. And though everybody knew the planet was there, they didn't know how to find it. It took another Parisian astronomer, Urbain Le Verrier, who worked in the same observatory as Bouvard, and he took these data, literally these data, and all the way up to 1840, and he used those deviations from where Uranus was in its position to pinpoint where he thought this new planet should be. He sent his prediction to the observatory in Berlin. The observatory in Berlin opened up their telescope, and in that very first night of searching, there was Neptune, right where Le Verrier predicted it should be. It's still, to me, almost gives me goosebumps. It's one of the most amazing moments of prediction and discovery and science that you can really come up with. And it was so amazing, even to people at the time, that Le Verrier became extremely famous. He was called the astronomer who discovered a planet with the tip of his pencil, and his name is engraved on the side of the Eiffel Tower, along with only 49 other eminent French people of the time. And not surprisingly, other astronomers saw this and said, I want to be famous too. I want to predict planets. And so starting really almost the next day, astronomers started predicting other planets beyond Neptune. Usually it was taking the orbits of Uranus and Neptune and saying that they too were still a little bit perturbed, and so there must be a massive planet further out there. And so between about 1845 and about 1930, something like 30 astronomers had predicted a new planet out beyond Neptune. And the most famous of these is one that most people know, and this is the prediction by Percival Lowell. Percival Lowell, who famously thought he could see canals on Mars and turned out to be wrong. Also, not quite as famously, predicted that there was a giant planet right outside the orbit of Neptune, about which he was also wrong. The reason he was wrong, it turns out, is because Bouvard back in 1820 was a little bit right. Astronomers actually needed to do better measurements. Uranus and Neptune are exactly where they're supposed to be. There is no need for a giant planet out there. But Lowell didn't know it at the time, and so he founded an observatory to go search for this giant planet. He passed away before it was found, but before he did pass away, he sent a team up to the Mount Wilson Observatory, which is just up the hill from where I live right here, and they took a picture of the sky, and it looked like this. And there it is. There's his planet X. Does anybody see his planet X? Well, no, nobody saw his planet X because, first off, he thought it was going to be huge. He thought it was going to be really obvious and it would cover a big blot of his photographic plate, and it didn't. So he looked at the photographic plates and went back to his drawing board and never saw his search to fruition. But he did found the Lowell Observatory in Flagstaff, and at the Lowell Observatory, they built a telescope whose job was to find this planet X. And they hired Clyde Tombaugh off of the farm to undergo this search. And he took a picture exactly like this one, not only exactly like this one, in fact, he took this literal picture. He took this picture and he looked at it and was like, how am I supposed to know what a planet is? Doesn't look like anything. But he was smart enough to realize, just like Herschel had done a century before, all he needed to do was take a picture the next day and watch it move. And there it was. Did anybody see it? I'm not sure you saw it. Let's try this again. There it is the first night. There it is the second night, maybe. Let's try the third time. First night, second night. Okay, last time's a charm. I don't know why everybody always gets it this time. Here's the first night. Here is the second night. These are the discovery images of Pluto itself. It is just like Herschel could tell that Neptune, that Uranus was well beyond Saturn. The astronomers at the Lowell Observatory could tell that Pluto was far beyond Neptune. And so it's not surprising that when they announced this discovery to the world, it was announced that the ninth planet was discovered on the edge of the solar system. First found in 84 years, lies far beyond Neptune. All of this is true. 25 years after Percival Lowell began, still true. Seen in Flagstaff, Arizona, also true. Astronomers hail finding, check. The sphere possibly larger than Jupiter. No, that part's not true. 4 billion miles away, yes, true. Meets predictions, also true. And that's the problem. The problem with the discovery of Pluto was that people were looking for a planet possibly larger than Jupiter. And it's a really interesting case history in science. It's the way that science can sometimes go wrong. The nice thing is that science has a way to correct itself, even though it can take a while. But when you're looking for a planet and you have a prediction that it should be over here somewhere, and you point your telescope in the sky and you find something over here somewhere that's beyond the only planet you know, it's hard not to think, I just found this planet. And it's hard not to think that it must be larger than Jupiter. Turns out, in case you were not sure, Pluto is not larger than Jupiter, and this is wrong by a factor of 250,000. The discovery of Pluto was just an utter coincidence. It happened to be approximately where Percival Lowell predicted it, but it is 250,000 times too small to cause any perturbations to Uranus and Neptune. They are not being perturbed at all. So astronomers at the time were a little bit confused by this, and they came up with all kinds of ideas why this tiny little thing actually had the mass of Jupiter, like it was made out of uranium and covered in an ocean of liquid oxygen and other crazy ideas like this. But the answer to why this tiny little thing looks so tiny is because It's really, 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 really small. The other interesting thing about it at the time, oh, let me show you how small it is. I forgot I had the slide in here. This is a plot that you often don't see. You often don't see the planets shown at their real sizes. You see them at what I like to call their lunchbox sizes, because my daughter had a lunchbox that was exactly like this, where all the planets are almost the same sizes, but everybody knows that Jupiter is the biggest one, so it's a little bigger, and Mercury is the small one, and it's a little smaller, but they're more or less the same size. They're not more or less the same size. They are, Jupiter and Saturn are huge. Uranus and Neptune big, but not nearly as large as Jupiter and Saturn. The terrestrial planets, Mercury, Venus, Earth, Mars, a good bit smaller, but still pretty big. And then you can see the asteroids in there too. And if we put Pluto on there, tiny, tiny little Pluto, it's kind of small. You know, it's hard to even see it if I didn't put it on there and didn't tell you, you might just miss it. But at the time, nobody knew what to call it. It was beyond Neptune. It's the only thing known out there. So people called it a planet. Who knew what else they could call it? The other weird thing about Pluto that was known even at the time was that if you look at its orbit, and here's the orbits of the terrestrial planets, Mercury, Venus, Earth, Mars there, Jupiter, Saturn, Uranus, Neptune. Pluto, as all of us know, is on this elongated orbit. It even goes inside the orbit of Neptune at some point. And if you turn the whole solar system sideways, it is tilted with respect to the planets in the solar system. It just didn't really fit either in size or orbit with what was going on out there. So even though it was called a planet for all those years, it was still this oddball at the edge of the solar system. All of this changed in 1992 when the second object was found beyond the orbit of Neptune, and then the floodgates were open. As of today, there's something like 3,000 objects known beyond the orbit of Neptune in this region of space that we call the Kuiper Belt. And the orbits of these objects in the Kuiper Belt, if you put them on the screen, they look a lot like the orbit of Pluto. They are elongated, they're tilted, they go this way, they go that way. They are basically a sort of bird's nest of objects out there going every which way. Finally, and this is why it happened, finally we realized the context of Pluto. Pluto does not belong in this system of planets on these majestic circular orbits, regularly spaced, regularly sized around the sun, but in this jumble of objects in the Kuiper Belt that is a fascinating collection of objects that I've spent most of the past 30 years now studying these objects, trying to understand what they tell us about the solar system. And they tell us a lot about the solar system. It's from these objects in the Kuiper Belt that we've learned how the solar system has rearranged itself. We've learned about the composition of the beginning materials. We've learned about giant impacts. And some of the things we've learned have come from some of the oddest objects that were found. One of the oddest objects that was found was nearly 20 years ago now, was this object called Sedna. Sedna is on a really peculiar orbit because, well, if you look at the orbit of all these objects in the Kuiper Belt, they're all pretty regular. And here, the ones that I'm showing here are all close into Neptune. They all come close to Neptune at some point, except for this new one, Sedna, new as of 20 years ago. Sedna is on an orbit that takes 10,000 years to go around the sun, which is weird. Even weirder though, it never comes close to Neptune. And yet, to be on an elongated orbit like this, we know that it had to have been pulled out of its normal, more circular orbit by something. All of these objects in the Kuiper Belt, we could explain by saying they were knocked around by Neptune. We can blame Neptune for a lot. Sedna never comes close enough to Neptune to have an interaction with Neptune. So we knew, the day we discovered Sedna, we knew that there had to have been other bodies in the solar system that were gravitationally tugging along at Sedna. At the time the discovery of Sedna 20 years ago, I was pretty convinced I knew the answer. I was pretty convinced that Sedna got pulled out of its orbit 4.5 billion years ago when a star came screaming by the solar system. And when the Earth was in its cluster of stars in which it was formed, and that star got a little bit close and pulled objects like Sedna out. And I knew if that were true, that I would find more objects like Sedna, and that they would show us kind of the fossil record of how things looked at the very beginning of the solar system. So this is pretty exciting. So we spent a decade looking for more things like Sedna? And the answer is they're rare. Here is a decades haul of all the objects that are sort of like Sedna. Not all of them are even like Sedna. Some of them actually come fairly close to Neptune, but they all have these very elongated orbits. And what's weird about all of these objects on these very elongated orbits is they all look like they're pulled to one direction. And they shouldn't be. And the reason they shouldn't be is because even if they were pulled to one direction at the time, 4.5 billion years ago, by a passing star, the directions of their orbits, if you think of them as hands on a clock, those hands all move at different speeds. And so they do, it's called precessing. They move around, their orbits point in different directions over the course of millions and billions of years. And because they move at different speeds, the chances that they would ever be aligned for any amount of time is minuscule. In fact, we could calculate the chances that these would be aligned like this just by luck is something like 0.5%. It's a pretty small number. It's not zero, because coincidences can always happen, but it's a really small number. So when we first realized what was going on, I keep saying we, the we in this case is my colleague Konstantin Batigan, who works just down the hall from me. And I took a plot like this down to Konstantin's office, and I'm like, this is really weird. They shouldn't be aligned like this. Let's see if we can figure out what's going on. And we both laughed at the time and said, well, it could be a planet, because that's the most obvious explanation. But we knew back then that was dumb, because 30 or 35 astronomers had been predicting that there had been a planet beyond Neptune for the last 150 years, and they were always wrong. And we did not want to jump up and down and say there's a planet and be yet again one of those people that are always gone. So it's wrong. So we spent a year working really hard trying to come up with other ideas that could possibly explain why these objects are pointed off in this direction. And in the end, strangely, we couldn't do it. We kind of felt like we were failures. We could not come up with another explanation other than a planet. And our idea was that a planet, well, okay, so we reluctantly thought about a planet, and we thought, well, what if a planet had a big orbit like this, elongated orbit too, and it kind of encircled all of the objects and kind of hugged them and kept them into place. That way, they would never cross the orbit of the planet. Crossing the orbits of giant planets is bad, and maybe they could be stuck forever. So we decided to try this out in a large computer simulation. And the computer simulation, oh, you know what? I was supposed to play this. I was going to show you one other interesting thing about these orbits. The orbits are not only elongated in one direction in the plane, but they're also, if you tilt these things to the side, they're also all pointed up just a little bit by about 15 degrees. So these things have been pulled by something, both away from the solar system and then out of the plane of the solar system. Pretty strange. So in our computer simulation, here's what we do. We take all of the planets. If you can barely see that little purple, pink circle right there, that's the orbit of Neptune. This is the orbit of the giant planet. It's elongated. You'll see its orbit, full orbit in here when some of these objects clear out. Each one of these blue things is what we call a test particle, where we put a Kuiper Belt object on an elongated orbit at a random orientation, and we let it interact with the planets of the solar system and this big planet. And we let it go for 4.5 billion years. And whoops, that's the wrong button. Let's try. No. There we go. 4.5 billion years, go. That button. Every one of these orbits that you see, you don't see the individual objects, you see their orbits as they change. And notice, first off, most of them are gone very quickly. Crossing the orbit of a giant planet is bad. Most of those objects rejected from the solar system. Objects that are close to the sun, by close, I mean still much further away than Neptune, but that don't really cross or barely cross the orbit of the planet, these are generally protected. You can see them doing that precession that I talked about. They're just going in circles at different rates around the sun. They're fine. The ones that we're interested in, though, are the ones that get stuck in this region here, like this one, this next one. Here's this one gets stuck. Nope. This one. No, this one. No. This one. Okay, I have bad news. Our idea was wrong. Nothing gets stuck in this region inside of the planet. Anything that gets into this region is quickly ejected. And the ones that get stuck, well, stuck is maybe not even the right word. The ones that are alive after 4.5 billion years are these on the opposite side of the giant planet. We scratched our heads for a minute thinking this is not what we expect. What did we do wrong? We reran everything, and suddenly we realized we were just being utterly stupid, and this makes sense. The reason these objects are still alive after 4.5 billion years is because an object on an elongated orbit like this spends most of its time out here or here or here. This planet spends most of its time out here. That means they're never, or they're rarely close to each other. When they come in through the inner part of the solar system, again, Neptune is here. So this is what I call the inner part of the solar system. When they come in through the inner part of the solar system, they're really fast. They come zooming in here like this and go back out again. These come zooming in here like this. So although they cross the orbit of the planet, they do it really quickly. And so the chances of being close are small. Consider instead an object that was out here on an orbit like this. It would spend most of its time here. The planet would spend most of its time here. They're close to each other most of the time, and those orbits are quickly perturbed and ejected from the solar system. So seeing these objects over here like this, or seeing these objects over here like this, told us not that there was a giant planet with an orbit like this, but instead that there's a planet on the other side of the solar system, getting rid, it's not really pulling everything, it's getting rid of everything else. And it's also tilted, just like the those objects in the Kuiper Belt are tilted. So this was fun. It was fun to come up with this idea and to say, okay, we now have an explanation for these weird things in the outer part of the solar system. But coming up with explanations is pretty easy. Astronomers do this all the time. You see something, you explain it. Doesn't mean it's real, but to really convince yourself that something's real, you want something better than explanation. You want a prediction. And our theory made a couple of predictions, and that was good. Some of them, while unexpected, we knew ahead of time, so we didn't quite count them. One of them accidentally is that we realized that having a planet like this, even though our goal was only to explain the way they were aligned, it also completely explains the way Sedna is pulled away from Neptune. A planet like this naturally does that to Sedna and other bodies like it. This was not something we tried to explain. So that's a success of our explanation. That was not something that we tuned in for. So that's good. But a better prediction is one where you didn't even know it. You make a prediction before you know it's true, and you wait and see if it's true. And so one easy prediction is there will be more objects found that are really distant, and they will be aligned in the same direction. And our actually detailed prediction is that they'll be about 90% aligned. There should be about 10% of the objects get stuck over here. We eventually found, but mostly they should be aligned over here. That's a good prediction, but that's a long prediction. It takes another 10 years to find more of these objects. Another really interesting prediction that came out of our computer simulations, though, was that there should be, in addition to having, I'm going to try to draw it here on your screen or on my face. If these are all the objects that are going in this direction, here's the orbit of the planet going in this direction. Sometimes these orbits get twisted by 90 degrees. So they're now perpendicular to the plane of the solar system. And then they also get twisted by 90 degrees compared to the planet and the other things. So they go here and they also go up here. They get to where they look sort of like wings on this pattern. It was interesting because we didn't think anything like that existed. And so it was a prediction we could make, but it was also, when we looked at, they should be relatively common. It was disturbing to us that we hadn't found any yet. So I started digging through some old data sets and looking at other objects besides just in the Kuiper Belt. And I suddenly realized that I had kind of been overlooking a set of objects. And these are ones that come actually closer than Neptune, but still go much further out. And there are not many, but there were at the time 5 of them on orbits perpendicular to the plane of the solar system. So I got Constantine to come over to my office, and I said, okay, there's 5. We predict they'll be in these wings. Where are they? We're either right or we're wrong. And the answer is, I didn't want to play that again. The answer is, here they are. The ones in blue are the 5 that are perpendicular, you can see, to the plane of the solar system. And they are exactly where we predicted they're supposed to be. They're in these wings to either side of this predicted spot. this was the moment when I think both Constantine and I, our jaws just dropped. We suddenly went from, haha, this is a fun explanation, isn't it cute? We can explain this with a planet, to, oh, I think there's actually a giant planet in the outer solar system. And I don't think I've had too much doubt since then. Since then, we have there have been other predictions and other things that have come true, and we can talk about some of those. The easiest one, though, is the prediction that more objects would be found in that same direction as the other clustered objects. And here they were. Originally there were 6. Now there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, I think is the number going in this direction. And I'm happy to say 1 going in the wrong direction, which is good. There should be at least 10%. That's close to 10%. Here's the orbit of the planet. The probability of finding all of these in this direction is now down to a fraction of a percent. It's pretty clear that there is that something needs to explain why these objects are tilted off in this direction. Also, some of these, not just Sedna, but several more of these are pulled away from the orbit of Neptune. Something needs to explain that too. This planet, which we now call Planet 9, is a very natural explanation for why we're seeing these patterns. I know it seems crazy, and the last 35 astronomers who said there was a planet out beyond Neptune were all wrong, and embarrassingly so. And so you shouldn't believe me when I say there's a planet, because I might be wrong and embarrassingly so, except we're right. There's a planet out there. There's kind of no other good explanation for why this would be going on. And a planet is just not crazy. We see other stars with planets out at those distances, and they would be making the exact same kind of patterns in their own planetary systems if we could see them close. So the only reason it seems crazy is because we've spent the last 150 years, 180 years now, being wrong about there being planets out in the outer solar system, and then convincing ourselves there aren't any. But I think there really were, still are. So let me tell you what I think, what we know about it. First thing we know is about how massive it is. The way we know about how massive it is because you saw that one computer simulation. We've done hundreds and hundreds of computer simulations at this point, and you tweak every parameter, make it a little more massive, a little less massive, a little further away, a little closer, and you can tune in to what it does to the Kuiper Belt and see what fits the data the best. And what fits the data the best, when we first looked at it, we hadn't done the computer simulations, we roughly said it was something like 10 times the mass of the Earth. Now we know it's more like, I say 6, I should change that. I think it's more like 7 now, if you ask me. As of this morning, the analysis I did, we'll call it 7. 7 Earth masses is really interesting. It's right between the mass of the Earth, which is precisely 1 Earth mass, and the mass of Uranus and Neptune, which are around 15. In our solar system, we have never seen a planet between Uranus and the Earth. And so we don't really know what they're like. And yet, around other stars, it's an incredibly common mass for a planet to be. 15 years ago, I would teach a class on the formation of the solar system, and I would talk about planets, and I would talk about our solar system versus other planetary systems. This was 10 years ago. And I would say, isn't it weird that we don't have any of these 6 Earth mass planets when they're so common around other planetary systems? But the answer is, I think we actually have one, which is pretty cool. So how big is it? Well, here's the planets again. Here's Pluto out there somewhere. Here's the rest of the Kuiper Belt, including the big ones that were found in a big flurry back in the early 2000s. Eris, Haumea, Maki, all sort of the same scale as Pluto, and part of the reason why we suddenly realized that Pluto doesn't really fit with the planets. It fits with these Kuiper Belt objects. This planet 9, at something like 7 times the mass of the Earth, is huge. It would be about this big. This is not a slightly larger than Pluto. Let's all argue about whether it's a planet or not. This is the 5th largest planet in our solar system, and it's waiting out there to be found. So let's go find it. How are we going to find it? Well, one thing we have to do is to know where to look. And that has actually occupied a lot of the last 5 of my years. We have done these computer simulations. We have tuned them up, compared them to how the solar system works. But then you also have to compare it to where everybody's looked in the solar system. And doing that, we've been able to construct a complicated statistical model of where planet 9 should be in the sky, how massive it is, how far away it is, everything you would like to know about it. And it looks something like this. So I'm going to show this map several times. So let me walk you through it so you know what it is. This is an all sky map. Imagine if you take a globe and squash it flat, so you see the whole globe on one oval. This is that same thing. The equator, the celestial equator, goes right across here. The ecliptic, where the planets of the solar system are, goes through here. And you can see immediately, well, the colored regions are the probability of finding planet 9 in any one particular place. So you see two things immediately. One is it's not in the ecliptic, it's tilted compared to the ecliptic. You saw that earlier, how everything's tilted like that. And the other thing you see is that it's most likely in this one region over here. And I'll show you why. Well, first off, I'm going to point out two more lines. These two lines here, this region in between here is the region where the Milky Way galaxy dominates the sky. So if you wanted to find something faint in the sky, you want it to not be in the Milky Way galaxy, there it is. Kind of irritating, but don't get to choose. So this highest probability is there inside the Milky Way galaxy. What else do we know about it? Well, here is how far away it is at all these different points in the sky. So if it's on an elongated orbit. So as you can see, its closest point to the sun is over here in the southern hemisphere. It's furthest away from the sun here in the northern hemisphere. And not surprisingly, the reason that this is more probable in this region here is because, as I said before, when things go around the sun, they spend more time at their distant parts of their orbit than at the close parts of the orbit. So it is most likely to be at its most distant parts of the orbit. You can see how distant that is over here in distances of AU. AU, of course, is the distance from the Earth to the sun. This goes from 200 to 2000. Neptune, by contrast, in the inner solar system is 30. So it's not even on this chart. So this is something like here is around 15 times further away than Neptune, quite a bit out there, but plausibly as far away as 1,000 AU, and plausibly the prediction is as close as 300. The other interesting thing here is that you get to see how bright it is in magnitudes. Magnitudes don't mean much to you if you're not an astronomer, so we'll walk you through that in a minute. But at first, I have to tell you, we know how massive it is. That's all our simulations tell us. It's the effect that we see as mass. We know how massive it is. We can then make a guess of if you are a 6 Earth mass planet, you are probably 2 times the radius of the Earth. This is based on what we see around other stars. We don't know if that's true for planet 9 or not, but that's our guess. The other thing we have to guess is how reflective it is. Is it made of clouds that reflect 100% of the sunlight? Is it made of coal, which reflects almost none? I think that it's most likely a giant planet like Neptune or Uranus, and therefore it's a cloudy planet, but maybe with some darkness in the clouds. And so we are guessing that it has a range of reflectivities between a very cloudy atmosphere that's very reflective and something that's darker than Neptune and as dark as, say, Callisto. So that's a pretty wide range that we're accepting. If we accept that very wide range, here is the range of brightness as it might be. And to calibrate your brain on what these magnitudes mean, backyard telescopes, I'm sure that there's somebody in the audience right there who has a backyard telescope that can see things that are like 19th magnitude, take a nice deep image of it. If your backyard telescope happens to be down here in the southern hemisphere, maybe you should be looking for it. Next, up here at sort of 21st magnitude, is like 100 modest-sized telescopes around the world could find it. Around here at 23, there are tens of really large telescopes. And up here at 24, 25, you really need some of the biggest telescopes in the world. So it's a pretty big range. Somewhere between your backyard telescope and the largest telescope in the world is what we need. Not clear which one it is. But the way to approach a problem like this is to start with the low-hanging fruit. The low-hanging fruit is the bright stuff. We have telescopic surveys that have been covering the whole sky, looking for things that move, looking for things that appear and disappear. And one of my favorite one of these, oh yeah, if it's up here, it's really, really hard. Oh, I don't have these plots. One of my favorite one of these is from the Zwicky Transient Facility that I don't know if anybody's heard of, but it's run out of Palomar, just down south from where I am. And it has ruled out already, just going to give you a quick feeling for what it's been ruled out. It's ruled out everything brighter than about 20th magnitude. So the easy ones ruled out. Next telescope to do a survey is one on Haleakala, on the summit of Haleakala on the island of Mauna Kea, on the island of Maui in Hawaii, and it has ruled out everything to about 21 and a half. That's right about here. So there's still some bright stuff left right around here, that bright, faint stuff left right around here, but we're in the tens of large telescope range. And we're also, as you might notice, there where the Milky Way galaxy is. And we're currently working on a survey of that region. Now, this is not data that exists that we can sort through like I was hoping to be able to do, but data we're taking ourselves. These data are from the Subaru telescope on Mauna Kea, which has a giant camera that can cover about this much sky all at once and get down to about 24th magnitude in our survey. So we've covered about half of this region. We're still analyzing the data, but we have another about half, in particular, the hardest part of the galactic plane half. We have this region in through here. So we are slowly ruling out the easy things. We're getting to the hard things. And if this doesn't work with Subaru and with all these other ones, the backstop is coming really soon. The backstop to all this is the LSST, the Vera Rubin telescope, which is now slated to begin operations in something like 2 years from today. And within the first year of the Vera Rubin Observatory operations, it will cover all but 2% of this whole phase space. It's in the southern hemisphere, so it misses some of the northern hemisphere. So it actually misses right up in here. So we're going to have to go and look at that very carefully, that last 2%, but everything else it'll cover. If we haven't found it by then, it'll only take a year of LSST to find by then. What if we don't find it then? I'm not sure. Somebody asked me this, like, when do you give up? When do you decide you are the 36th and 37th astronomer to say there's a planet and be wrong? And I think the answer to that question is when there's a better explanation for all of the phenomena that this planet can currently explain. And until there is, this remains the best explanation. And if we don't find it, I think it's not because it's not there. I think it's because something in our assumptions about making our predictions were wrong. Maybe it's further away than we thought. Maybe it's actually even darker than we assume. Maybe it's smaller. Maybe it's not a gas giant. Maybe it's a big ice ball, a dirty ice ball, so it's dark. There are these other possibilities. So we will keep going, and we actually are working on other ways of trying to find it beyond just optical telescopes. But until there's a better explanation, or even an as good explanation, I really think this is the hypothesis to beat. And I really believe that if not sooner, that within the next 3 years after the first year of the Vera Rubin Observatory operations, I don't see any way that this planet can be hiding anymore. I'm going to leave you with where I think it is. I think it's hiding here in the galactic plane, where it's the hardest to see. And that region of the sky, it's just a spectacular region of the sky. It's close to everybody's favorite place in the sky. Everybody's favorite place, whether they realize it or not, is somewhere where in the winter sky, constellation of Orion, constellation Taurus, this cosmic battle between the hunter and the bull here in the sky. The path of Planet 9 goes right between, though. It could be sitting right around here right now, although as you can see the more stars up in here. This is where the Milky Way galaxy gets thicker and thicker. I bet it's right up here, kind of sitting on the head of Orion. Orion's not really up yet this time of year, but even just in a couple months, it's going to start to be up in the morning skies. And what I want you to do, if you're ever up on one of these early mornings and you suddenly see Orion for the first time in the year, it's always kind of a magical moment for me, seeing Orion for the first time in the year. And I feel this chill of winter coming in, even though it's still late summer. But I want you then to look up at the head of Orion and look up there. And I want you to just imagine that this planet is really there, and it's really out there, and it's waiting to be seen. And I'm just going to end with the poster that I came in at the beginning. And I hope a few people at least recognize this. This is a photoshopped version of the poster from Plan 9 from Outer Space. Plan 9 from Outer Space famously declared the worst movie ever made, directed by Ed Wood in 1959. I mean, it's bad. It's actually on Wikipedia, just Wikipedia Plan 9 from Outer Space. I dare you to try to watch it. It's got Vampira and Bela Lugosi. It's Bela Lugosi's last movie, but he died before they actually finished it. So they only have a couple of scenes of him doing weird, crazy things. It's got zombies. It's got aliens. I mean, it's pretty bad, but it's Ed Wood. Ed Wood is also, of course, known as a genius director, and sure, he was a genius director, but I think he was a genius in other ways too. And one way is really clear on this poster. If you look at this poster really carefully, there's a graveyard scene where they're digging up the zombies or the aliens or something. And if you zoom in here to the graveyard scene, you look really carefully and look at that tombstone. There it is. Ed Wood put it on 1959. He knew something was going on. R.I.P. Pluto. Even then, he knew it was not a planet. Thanks. And I'm going to end now, so I have plenty of time for questions.
Yeah, so if everybody would like, if you have questions, please use the Q&A function, and we'll go ahead and try to sort through these in a little bit of an order as we can. Katie Kitten Mama has had a series of questions, so we're going to kind of condense them all together. First of all, said your graphics are gorgeous. So
thank you.
And with that, they said instead of ninth planet, could our sun be a binary? And an addendum to that was, or I'm sorry, that's the question first though. Could our sun be a binary?
Yeah. So this was something that people have been really interested in for decades, and there's been a lot of research, a lot of careful scanning the skies, looking for, like a brown dwarf really far away that nobody's seen before. And it's been really quite carefully ruled out that there's another star anywhere in orbit around the sun. So that's part A of my answer to your question. But part B is, in our case, it's definitely can't be another star, even a brown dwarf, even something as large as Jupiter, because if it were, it would make a very different effect on the Kuiper Belt. If it were close, it would tear the entire Kuiper Belt apart. If it were further away, it would have a very different effect. So we can really we can constrain the mass of this planet quite nicely. It cannot be nearly as massive as even the smallest of brown dwarfs. And let me just answer the other part of the question there, but about circular orbits versus elliptical. I did say planets are on circular orbits. They're on orbits that look circular to our eye, but you're absolutely right. Planets are all on very mildly elliptical orbits to kind of elliptical orbits. Mercury and Mars are moderately elliptical, but by eye they still look pretty circular. But the objects in the Kuiper Belt and now Planet 9 are on elongated to very elongated orbit. So it's, even though they're all elliptical, there's a sort of matter of degree about how much more elliptical those are.
All right. So someone asked, anonymous attendees, and maybe I missed the part, but what makes you right about Planet 9 and those other 35 previous astronomers wrong?
It's an excellent question.
I like it a lot. Yeah.
So, I guess the answer is we're just better than they are. No, that's so first let me tell you why they were all wrong. They were all wrong for one of two reasons. And sometimes both. Wrong reason number one is bad data. Percival Lowell, for what it's worth, had data that suggested that Uranus and Neptune were being perturbed, and he used those data to predict where his planet was supposed to be. Turns out the data were bad, so he was wrong. His calculations were actually a little bit wonky too, but we won't complain about that. His data, even if he knew exactly what he was doing, his data would not have let him predict a planet, because Uranus and Neptune are, as far as we can measure, exactly where they're supposed to be. There's another reason astronomers have been wrong, and that's not because there's bad data, but because they have bad physics. The most famous of these, I mean, bad physics sounds judgmental, but the most famous of these is Leverrier himself. After finding Neptune, turned around and decided to try to understand if there were any other planets inside the orbit of Mercury. And he looked at the orbit of Mercury, which is precessing faster than it should. That the elliptis, the direction of its orbit is moving, precessing faster than it should, which is absolutely something that a planet would do. And he predicted that there's a planet, he called it Vulcan. This is the origin of our superstition, which is never name a planet before you've seen it or you won't find it. He predicted planet Vulcan and he was wrong. The reason he was wrong was because he didn't know about general relativity in 1850 when he did this. And that's why Mercury's precessing. So he was wrong. Pretty good reason though. I mean, his analysis helped point the way towards general relativity. But in those ways, all the astronomers have been wrong. Often it's been bad data has been the main thing, but sometimes it's been Leverrier had good physics that was wrong because we didn't know, we had to learn new physics. Other people have had pretty iffy physics and not done it really well. So the question to ask yourself then is, are our observations wrong? And is our physics wrong? The physics is the easiest one to answer. Unless there's something weird going on in the solar system and we're about to discover something new about physics, which by the way, I'd be happy to be wrong for that reason. That'd be kind of fun. But unless that's the case, the physics is easy. It's 1 over r squared. We can do gravity. So then the question is, are our observations wrong? That's actually the most interesting question to ask. Now you can look at those observations I showed you and it's like, yeah, they're all pointed off in this direction. But what if it really is just a coincidence and we're fooling ourselves? What if it's more a function of astronomers have only looked mostly in one direction and not another? We've spent a lot of time poking at that exact problem and trying to make sure that we're not fooling ourselves. And other astronomers have been poking at that too. And we have, I think, made a very convincing case that really what you see is what you get. The objects really are pulled off in one direction, and there's nothing that we're fooling ourselves in. It's again something that the Vera Rubin Observatory, LSST, is going to prove very well with its surveys of the whole sky. We will find many of these objects. There'll be no doubt that these are pointing off in one direction. So if the physics is right and the observation is right, the only other thing that be going on is that there is a different explanation that can explain those observations. To date, no one has come up with one that works. Doesn't mean that they won't, and doesn't mean that eventually, somebody won't show that there's something that works and we are wrong. But astronomers love coming up with explanations that they can show to people and say, oh, those other guys are dumb and wrong. So far, nobody has been able to come up with something to show that we're dumb and wrong. And a lot of people would love to. So far not. So that's why I'm convinced. People are skeptical. Everybody should be skeptical, but that's why I'm convinced.
Excellent. So one question here from Aaron said, could the James Webb Space Telescope be of any help?
So yeah, I promised I would mention about James Webb. So James Webb, if you saw the picture that James Webb released today, it covers about this much sky at once. Now, if you gave me all of the time on James Webb for the next 20 years, I could use it to cover the entire sky and I would find Planet 9. So it could, but I don't think they're going to let me take it over for 20 years to do this search. I think other people want to use it for their science too. I don't know why, but I think it's true. Nonetheless, as soon as we find Planet 9, one of the very first things we're going to do is call up JWST and say, we just found a new planet. Can we take your big fancy telescope and point it at our new planet? And they will say, yes, you can. And so we'll get a spectrum of it with James Webb, which will tell us what it's made out of, what's in its atmosphere, maybe where it came from, and other things like that. So it's going to be a very important tool in the study of Planet 9 once we find it.
To piggyback off that, do you know or have an idea of what this planet would look like, whether it be solid and rocky, a smaller gas giant?
Yeah. So as I said earlier, we know its mass, 7 Earth masses. In the rest of the galaxy, 7 Earth masses seems to mean a body like Uranus or Neptune. So that's our best guess. But it doesn't mean that we're right. Around the planets around other stars that we're seeing are much closer in and much warmer. So maybe there are icy planets that are much further out, and this is one of those. We don't know. So that's one of the fun things about finding it will be to get to learn all these things about it for the first time.
All right. It said Luke asks earlier, you talked about the predictions and observations of smaller objects similar to Sedna. If you were able to make predictions for these objects, what are some possible reasons for why it is so hard to find Planet Nine, which should be much larger? Is it just the location in the sky, or could it be the inherent problem with the planet itself?
Yeah, a couple different answers to that question. One is I showed you the orbit of Planet Nine, and we think, as I said, it's on the outer part of its orbit. The Kuiper Belt objects, we find them all in the inner part of their orbit, so they're much closer than where we think Planet Nine is. So that makes them much brighter. So Sedna, these other objects are 20th magnitude, 21st magnitude, 23rd magnitude. Planet Nine might be 23, 24. So it's faint because it's so far away. The other thing that's hard about it is that the reason we can find Sedna and other objects like it is because there are many of them. And so we can cover a random patch of the sky and we might find one. And we cover another random patch, we might find one. But if you only cover, if you have only one object in the sky to find, it's a needle in a haystack, and it's not even a needle in a haystack. It's a grain of sand that I have taken and thrown onto the beach and told you to go find the grain of sand on the beach, because it looks just like any other grain of sand on the beach, but you have to go find it. So that's the hard part.
Gotcha. All right. Well, we're going to do one last real short, quick question here. Are the objects like Sedna from the Oort cloud or the Kuiper Belt?
So we used to think they were from the Oort cloud. We are now, because we understand how Planet Nine does things, we now realize they could be pulled out from the Kuiper Belt in a very standard way. So we think that they're from the Kuiper Belt, but it's not impossible that some of them or all of them also get pulled in from the Oort cloud. And interestingly enough, that's actually it's a question that's actually keeping us up at night, or I should say keeping us up in the day, because telescopes keep us up at night. But it keeps us up in the day because my entire theory of where Planet Nine is based on objects being pulled out of the Kuiper Belt, not being pulled in from the Oort cloud. And if they're being pulled in from the Oort cloud, it kind of changes some of those parameters. So we're redoing our predictions, and I'm worried it's going to make it be further away and harder to find. But we will find out, and stay tuned.
Gotcha. All right. One last one, purely for the audience. In 2006, Wired Online listed you as the top 10 sexiest geeks. Has your wife let you live that down yet?
Her usual statement is it was a slow year for sexy geeks.
Excellent. Well, thank you so much, Mike, for being here. We appreciate it. Loved your talk, and we're going to keep following you in hopes that you find our Planet Nine.
Thank you so much. This was great fun.
All right. Excellent. How you have a great night. And again, thank everyone for being here. And we appreciate all of you. Tune in next month. We'll be announcing our guests here in the next few days. So thank you and have a great night.